we can introduce quantum field theory through canonical quantization. In this case, we start by posing a commutation relationship at equal time between the field and its canonical momentum. And now that we impose that these two objects do not commute, they cannot be simple number anymore, they have to be represented by matrices, and in quantum mechanics that can be abstracted in terms of operators. So the field are now operators in canonical quantization, which means that when we take the free Hamiltonian scalar field theory, so we start from the Klein-Gordon Lagrangian, we take the earlier Lagrange equations, which gives us the classical equation of motion, but now we quantize them by requiring the field to be an operator. So the Klein-Gordon equation is now quantum because phi is an operator. The solution of this equation is given as a function of plane waves. So we have a sub of plane waves with A and A dagger operators, which obeys this commutation relationship in order for the initial commutator between phi and pi to hold. From this we can build the Hamiltonian, which is a space integral of a Hamiltonian density, which we obtain using Noether's theorem. In the case of the Klein-Gordon Hamiltonian for free scalar fields, we got a sum of harmonic oscillators with a dagger creating a particle with energy omega k and momentum k, and that's if we choose A, the action of the annihilator on the vacuum to give 0. So that's defined by the vacuum being here the vacuum of particles, but that's a freedom we have. The field phi of x, when applied to the vacuum, creates a particle, and that's because it has an A dagger in it, and it creates it in x if according to the non-relativistic interpretation. In the case of relativistic particles, this is a bit more complicated, but we still usually keep this interpretation that phi of x create a particle in x. It also annihilates one because there is an A part, so an annihilator, which kills a particle eventually which is in x. But when it acts on the vacuum, it can only create one. So we have now all the information to describe and compute elementary process like this one when we have a collision of particle-antiparticle creating new particles-antiparticles. In fact, we didn't need canonical quantization to calculate elementary processes like that. We did all that using path integrals. We introduced canonical quantization motivated by the question of how many particles are associated with the disturbance of the field. And this we got by questioning how much energy is carried by a disturbance of the field. And this turns out to be easier to answer in canonical quantization. But keep in mind that canonical quantization and path integral approach are fully equivalent, and we will see that eventually by comparing the propagators for disturbance of the field in one case and the other, and see that they are indeed the same. And there are other questions which are easier to answer in canonical quantization. So one of them, for instance, is what happens with the causality problem which we had at the beginning, which was one of the motivations to introduce quantum field theory. So we will address this point now to verify that yes, our quantum field theory doesn't break causality, unlike relativistic quantum mechanics. And we will also see a version of the spin statistic theorem, which tells us that half-integer particles are fermions, while integer particles are bosons. And we will do that by repeating what we did for Klein-Gordon, but now for the Dirac field. And we will see that we have to change this commutation relationship, and that will give us the Pauli principle. So it's not the most general proof of the spin statistic theorem, because in this case it only works for given Lagrangian. So you have to assume what is a Lagrangian, and then you can work out if the particles behave as fermions or are bosons. It's not as general as when you start by a completely arbitrary Hamiltonian and just require causality in order to get the connection between spin and statistics